In the previous lecture, we talked about Bohm-Hammer approximation and adiabatic approximation. The adiabatic approximation is actually quite general in quantum mechanics. In this lecture, we will talk about the general theorem of adiabatic. The first concept I want to discuss is adiabatic invariant. Let us consider a one-dimensional classical harmonic oscillator. The angular frequency of this harmonic oscillator is changing with respect to time. So the classical Hamiltonian is H is the kinetic energy plus the potential energy. Now, in this case, we consider the angular frequency as a function of time. So in lecture 1, we talk about the equation of motion. So if we study dH dt, we will have H, this is the classical Poisson bracket, plus partial H, partial T. And this is, of course, is simply partial H, partial T. And the time dependence comes from the time dependence of omega. And this will give you m omega of t times d omega dt x squared, right? So suppose omega t versus t looks like something like this, okay? So starting from a particular instant, let's call this instant 0. And from 0 to tau, you have a changing omega, okay? So, well, if we look at a very tiny interval, so within this interval, the vibrational periodicity can be approximated as 2 pi over omega t. At this particular point, this is, say, t, or we use t prime here. So at this particular point, t, the corresponding omega is omega of t. And because we're considering a very tiny interval here, so, well, we can reasonably approximate the vibrational periodicity within this small interval being equal to 2 pi over omega of t. Now, what is adiabatic? Adiabatic means adiabatic change means tau is much larger than t. That is, omega is varying slowly. What do you mean by slowly? Slowly means the value of tau can be viewed as much larger than t. Tau, of course, is the time scale of the external change, right? This is right? This is tau. T is the vibrational periodicity. This is the intrinsic motion. That means this external change, the time scale of the external change is much, much longer than the time scale of the internal motion, the internal vibration. Now, let us consider this quantity, I, defined as the total Hamiltonian over omega of t. Let's investigate what is di dt. What is the time dependence of I? Di dt is, of course, 1 over omega squared, omega times dh dt, minus h times d omega dt. And this is equal to 1 over omega squared times omega times, what is dh dt? Well, we already figured out dh dt is equal to m omega d omega dt times x squared. Minus h, kinetic energy, plus the potential energy times d omega dt. Right? And you can pull out d omega dt, so you have d omega dt over omega squared, and this is 1 over 2 m omega squared x squared minus p squared over 2m. Right? And this is d omega dt over omega squared, potential energy minus kinetic energy. Now, for the harmonic motion, the potential energy minus kinetic energy is, of course, 1 over 2 m omega squared. What is x? If you solve for the equation of motion, for harmonic motion, x is a sine omega t squared. Let us choose the initial phase angle being equal to 0. Minus p squared over 2m. P is dx dt. X is a sine omega t, and therefore p is a m omega cosine omega t squared minus this divided by 2m, right? And this is equal to negative 1 over 2 m omega squared a squared cosine 2 omega t. All right. So let us look at this integral. Within single period, I, this quantity t plus a periodicity minus I of t is equal to what? Within this period, then we have, well, because we know di dt, right? We already know what is di dt. Di dt is equal to this. And the difference between the potential energy and the kinetic energy is equal to this. And therefore, we can have an integral from t to t plus periodicity di dt dt, right? And this is basically, if you ignore some constant, then this is basically t plus t d omega dt times cosine 2 omega t dt, right? And as we said, if we consider an adiabatic change in which omega varies slowly, so we consider omega varies slowly. So within this interval, actually, this d omega dt can be considered as a small constant. Okay, so it is indeed varying with respect to time, but it's very, very, very slowly, such that the whole process is adiabatic, right? Within this small interval. And therefore, it plus t minus it is basically, well, since we basically approximate d omega dt as a constant, then you can put out d omega dt in front of the integral sign. Then you have t plus t cosine 2 omega t dt, right? And this is, of course, is equal to 0 because capital T is the periodicity of this function, right? So in general, this is basically 0. That means this quantity, which is defined as the total Hamiltonian over omega, is almost a constant. Not rigorously, but approximately a constant under the adiabatic change of omega, right? So we call this I as the adiabatic invariant. Right? I basically is a constant under this adiabatic change of the angular frequency. And this is called adiabatic invariant. Now, in lecture 1, we also talk about the phase space. So of course, in phase space, for one-dimensional harmonic oscillator, this is very simple. So you have x and the momentum. So the phase space is basically an ellipse, right? So you have a V here. So the area of this ellipse is pi times A times B, right? This is pi times what is A? A is 2e over m omega squared, square root. What is B? B is 2me square root. And this gives you 2 pi times e over omega. And this is equal to 2 pi I, right? Based on our definition, I is the total Hamiltonian over omega. And for a conserved system with a natural choice of the coordinate, the H is simply equal to the total energy. And therefore, total energy over omega is our adiabatic invariant. And that gives you, this gives you what? This gives you 2 pi I is equal to, well, this is the area of the ellipse. That is the integral P dx, right? This is the phase space integral over a closed loop, right? This is area of an ellipse. Of course, this P dx is used in the Sommerfeld quantization condition, right? So, okay, let's see quantum mechanically. If we still use the same definition of the adiabatic invariant, so this is defined as total energy over omega, then of course we know for a one-dimensional harmonic oscillator, the total energy is m plus 1 over 2 h bar omega. And therefore, quantum mechanically, this adiabatic invariant is equal to m plus 1 over 2 h bar. N, of course, is the quantum number. And that means this P dx is actually equal to what? 2 pi I. This will give you m plus 1 over 2 h, right? H bar is h over 2 pi. H is just the original Planck constant. Of course, if you remember what we have talked about in lecture 1, this expression should be very familiar to you. If the quantum number is very large, say n is much larger than 1 over 2. This is actually the classical limit. And then you have simply P dx, this phase space integral is equal to nh. And this is exactly the Sommerfeld quantization. So the Sommerfeld quantization condition is almost right, but not quite, right? Qualitatively, it gives you the big picture of the quantum mechanical system, right? Especially if the system quantum number is very large, then this semi-classical quantization condition can give you very good result, right? Another remark that we see here is, you see, the adiabatic invariant is basically characterized by the quantum state or by this quantum number, n, right? That means classically, we know I basically doesn't change with respect to time under an adiabatic process. And quantum mechanically, the adiabatic invariant is characterized by state n or by the quantum number n. And therefore, we can say quantum number n or quantum state, which is characterized by this quantum number n, does not change under adiabatic change. This is actually a very general observation, and this is very important. And this gives us the adiabatic theorem. I should say, this observation, right, the connection between classical and quantum dynamics This observation motivates us to propose this adiabatic theorem. Of course, we haven't proved this adiabatic theorem. So the adiabatic theorem states that if the system is initially, that is at time being equal to 0, or you define the 0 of your time in the eigenstate, and usually an eigenstate is quantized by some quantum number, right? Then it remains, this system remains in this eigenstate at time t under adiabatic change of the Hamiltonian. Okay, the Hamiltonian is changing, so it's actually a time-dependent Hamiltonian. But if this adiabatic change, if we consider an adiabatic change of h, then the system remains in its original eigenstate at t being equal to 0 at other time t. And the wave function although you still basically remain in this state, but the wave function are not exactly the same. The wave function picks up a couple of phase factors. Of course, this will, in a lot of cases, this will not alter your observation, right? But we will see that in some cases, these phase factors are very important. But the adiabatic theorem tells you that if you consider an adiabatic change of the Hamiltonian, then the system remains in its original eigenstate. Its wave function differs at, if you consider the wave function at time t and at time 0, the difference is only about a couple of phase factors. All right. Next, we will talk about the proof of this adiabatic theorem.